We built a cryptographically non-secure hash function. We have two tasks at hand, basically. The first is estimating how many quantum resources we need to implement the cryptographically non-secure protocol. And then we have to throw a cryptographic obfuscation technique so that it becomes cryptographically secure. We cannot just use any obfuscation method. We need to use quantum-resistant obfuscation methods.
Scraping Bits is brought to you by the following sponsors. MEV Protocol. Maximize your ETH staking value with MEV ETH, exclusively on mev.io. And Composable. Execute any intent on any chain, coming soon to mantis.app. That's mantis.app. And Fastline Labs, the only MEV and intent-centric team that has a daily deodorant application rate of over 68%. GM everyone, my name's Dagachi, the host of Scraping Bits, and today I'm with Fabrizio from 20 Squares. How's it going, GM?
Hello, GM. It's going nice. You?
Yes, not too bad. Just moved into this new London house. Bit busy, but we're finally here. Just for the people that aren't familiar with you, who are you and what do you do?
First of all, thanks for having me. Basically, I work at 20 Squares. That is a company working, around MEV, modeling and analysis in crypto, especially focused on economics, game theory, and mechanism design. We do a pretty wide array of things, I would say.
Nice. And one of the things you're working on now is actually quantum one-shot signatures.
Quantum one-shot signatures, yes.
Yeah.
That is basically something a bit different from what we usually do. That is connected to the fact that in a past life, I was a quantum computing scientist. I have a PhD in quantum computing. So in a way, this kind of like the past came back. And now I'm working in bringing Ethereum and in particular the quantum infrastructure closer together.
Definitely. How did you get into quantum computing? Because I think it's a fairly hot topic now with people thinking about AI in the next generations, needing quantum computing to, I guess, achieve this quote unquote AGI, but also in cryptography as well. So how did you really get into this? I think it's a very niche field, right?
I got into it by chance, basically. So I applied for a PhD. I graduated in mathematics and I applied for a PhD at the University of Oxford. I started in 2015 there. And basically the way it works is that you say vaguely what is that you want to do, and they find a professor, they pair you with a professor. This guy writes back, and almost always it's something like, I don't do exactly what you want to do, but I do this thing that is kind of close. Are you interested? And then they interview you, et cetera, et cetera, et cetera. And basically, my former professor, Bob Kuke, which now is a lead scientist at Quantinuum, that is is the biggest producer of verticalized quantum hardware and software. But basically, he contacted me and said, hey, I don't know what is that you want to do. I want to do something about logic. It's like, I don't do this stuff. But what I do is categorical quantum mechanics, which is basically category theory and quantum mechanics. Are you interested in that? And I'm like, well, I don't know any category theory and I don't know any quantum mechanics. So this seems perfect. And I obviously said yes. And I had a hellish first year, trying to pick up and study all these things. And then it was actually very interesting because the whole spiel of this thing is doing quantum mechanics using pictures, using diagrams. So there is this kind of mathematical framework called category theory that allows you to abstract the mathematics away. So quantum mechanics uses a lot of algebra. It's mainly linear algebra all over the place. And this kind of thing allows you to do quantum mechanics, but without seeing this underlying linear algebra. You do it with pictures. And by the way, this is something that we are also heavily using in this quantum one-shot signatures research. I'll probably try to touch about it later on.
Quantum mechanics is very interesting. I remember seeing some TLDR on it, and correct me if I'm wrong, but it's basically finding, I would say, vulnerabilities in the atoms of the universe. Nuclear power, for example. You're just finding these vulnerabilities and then harnessing it for its power. Is that kind of accurate TLDR, or maybe you can do something more in depth?
So, yeah, I think there are a couple of things that happen in quantum mechanics, which are very interesting. The first one is that basically in quantum mechanics, you do not know with certainty what is going on until you perform a measurement, until you choose to observe something. Before then, your particles or whatever it is that you are working with is in an indeterminate state where it can be multiple things at the same time, and you reason probabilistically. So when you do like a quantum mechanical experiment, the physics gives you probabilities. Then you perform the experiment like 1,000 times, and every time you have a deterministic result, but then these kind of occurrences align with the probability spectrum that you predicted. So like you will have like, okay, 10% of the cases will be this, like 50% of the cases will be that. And then you check that this is what you had in your probability related predictions. But the important thing, which a lot of people miss, is that it's not just that things are in the same, like in an indeterminate state, and like a bit can be 0 or 1 at the same time and stuff like that. Because if that was the case, probabilistic computing would be enough. That it's basically algorithms where at some point you flip some coins or you have some probability distribution, some randomness in your algorithm. The point is that in quantum mechanics, you have that these probabilities have amplitudes that are expressed as complex numbers. Now, if we want to be like absolutely simple, imagine that you have 2 points, 0 and 1. Those are your bits, right? That your bit can be 0 or 1. In probabilistic computing, you would say that a bit can be anything in the middle. So you draw a line between these points, and if you are in the middle, then you are like, okay, this can be 50% of the times 1, 50% of the times 0. So you have a 1/2 probability of going either way. In quantum mechanics, you don't have the line. You have a sphere. So you have a sphere. The North Pole is 0. The South Pole is 1, for instance. Basically, wherever you are on this sphere, the closer you are to one of the poles, the more likely it is that you will collapse to that pole. But if, for instance, you think about the equator of the sphere, those are all possible states that are equiprobable. In that case, you have, 1/2 of the probabilities that the result will be 1 when you measure, and 1/2 that it will be 0. But you see that you can perform operations, that you can rotate your qubit on this surface of these spheres. And like a rotation around the equator basically doesn't change the final probability when you measure. So this is not seen by the measuring process in a way. But that is exactly what makes it very powerful, because you can do these sort of like quote unquote hidden moves. And then you combine this with entanglement, which is basically the procedure that makes particles or qubits or whatever it is that you're studying correlated. And the idea of entanglement is that when you entangle like 2 qubits, that basically whatever you do on one influences what happens on the other. Again, you can use this thing in a very powerful way.
And what is a qubit?
A qubit is exactly the sphere I told you before. So technically, a qubit is, you can express it as a vector in C2. So a vector in 2 coordinates. Each coordinate is a complex number that must be normalized. That basically means that this vector needs to have length 1. That is like the most probably like cursory way of defining what a qubit is. But yeah, it's the analogous of a bit for quantum computation. So a bit is a couple of points. A qubit, as I said, is basically a point on the surface of this sphere.
Right. So now that you're into quantum one-shot signatures, let's start off by saying, what's the difference between, a quantum signature and a classical signature?
Yeah. So, okay, the important bit here is that quantum one-shot signatures are a primitive that allows you to use something to sign a message only once. So with standard cryptography, information can be copied. So if I have a private key and I use it to sign a message, I can reuse the private key to sign another message as well. In quantum mechanics, the idea is that you tie the private key to a quantum thing. So your private key is a quantum state, and the act of using this private key amounts to measuring this state. Now, when you measure this state, again, think about the sphere. Measurement means that your point on the surface of the sphere collapses to one of the poles. So the information of where that point was is lost forever. This is a destructive process. So basically, this allows you to use this private key only once. And after you use it, the key self-destroys. And it's basically impossible to reuse it for pretty much physical reasons. So with this thing, we can solve a lot of interesting problems where maybe you want to delegate someone to, I don't know, spend your money or something like that, but you want to make sure that they do it only once. So you want to delegate another person to sign a message on your behalf, but you want to be sure that they can only sign one message, and you want to give full delegation. So you don't want to set any precondition on the message they need to sign. And that's what quantum one-shot signatures allow you to do. And this research made its way into crypto basically 1 year ago, I would say. Because if I can digress a little bit, at last ECC in July, there was a very interesting coincidence. 15 minutes on foot by the main ECC venue, there was QPL going on. QPL stands for Quantum Physics and Logic, and it is a quantum conference. And that was my old conference. So when I was a PhD student, I would regularly go there and submit papers there. So it was literally like my old crowd and my new crowd very close. And I'm like, okay, this is a very, very nice coincidence. We have to do something about it. So I spoke with some people to organize something, and friends at the EF, notably Barnaby, say, you should talk with Justin Drake because Justin is, looking into quantum stuff, is interested in this stuff. So we started talking, and we organized a panel at ECC where we invited speakers from QPL, and we had this discussion, and quantum signatures popped up. Then we hosted an event like a couple of days later, organized by 20 Squares and hosted by Flashbots at the Flashbots house. Lots of people from QPL and the Ethereum ecosystem came, and we started brainstorming more about this stuff and its possible utility. And then this January in Edinburgh, the Ethereum Foundation, together with the Cardano Foundation, created an event, a workshop called QSIG, where, we had talks and discussed this thing. And since then, we've created basically an organization on GitHub that is called the QSIG Commission, which has the purpose of researching these quantum one-shot signatures more in depth, because it turns out that they give you amazing properties, especially at the level of consensus protocol. So there's this property of consensus called finality, which is very important. Finality is basically when a block is final. So if that block is final, it cannot be changed, and it's like a checkpoint. The blockchain up to that point becomes really immutable. Now, at the moment, in Ethereum and in Tendermint and in a lot of other protocols, we have the concept of economic finality. Economic finality basically means that these blocks are final because it's super expensive and basically economically non-rational trying to change it. You should hijack all the validators, get consistently, I think, more than 66% of the validating crowd, et cetera, and spend an unfathomable amount of money to kind of be able to hijack finality. So there are economic incentives that make the chain final. Quantum one-shot signatures instead make the blockchain perfectly final, which means the chain is final because of physical underlying principles that guarantee you that. It's like saying it's gravity that now tells you that the blockchain is final.
Instead of someone else.
Yeah. And by the way, the way this works is actually pretty simple in a way. So the main idea of a quantum one signature is this. You have a quantum computer. This quantum computer computes a hash. It's literally just a random value. Then basically you give some bits to the quantum computer. So for instance, a message, and the quantum computer will compute the kind of end that needs to be attached to this message so that the message plus the entropy hashes precisely to the value calculated before. So it's like you are inverting a hash effectively. But the cool thing is that you can do it only once. So you invert the hash and you can do it only once. If you cannot repeat this procedure with the same hash. So the way this works is the quantum computer produces a hash that is, again, a physical hash. So something very, very classical. The validator signs this hash and says, okay, I see it. Then what the validator does is, when they vote, give their signed message to the quantum computer, and the quantum computer outputs some entropy so that message plus entropy gives the hash that the validator committed to. And now the point is, if the validator equivocates, so the validator signs two conflicting messages, the quantum computer will be able to validate only once, only one of them. So, because, if I say, okay, I'm giving you two different messages, the quantum computer can calculate the pre-image, the entropy, so that this message becomes a pre-image only once. So it cannot do the same thing for both messages. It has to pick one. And so in a way, it's like your quantum computer is now putting like a stamp and it's saying, this is what the validator voted, and that's it. And the super cool thing is that the validator doesn't need to have access to any quantum resource whatsoever. You need one quantum computer on the whole fucking planet, and that's everything you need. Then all the rest can stay the same. All validators can be classical. Like nothing changes there.
Oh, so not every validator needs a quantum computer then. That was interesting.
If that would be the case, this would be incredibly unfeasible. But that's exactly why it's interesting. No, you don't need that. The quantum computer will spit out a classical hash, a classical 256-bit string. Validators will sign that bit string. They will send the message to the quantum computer, and the quantum computer will spit out another bit string, again, classical, that is the entropy. And the hash function that is used is a classical function so that everyone at home can take the validator signed message, the entropy provided by the quantum computer, and check that, these hashes to the value that the validator committed to. So yeah, that's why it's great. Like everyone with a classical computer can take part. We just need one quantum computer on the planet to make this possible.
But if we had all the validators relied on this one quantum computer, then wouldn't that be prone to at least, like if that got shut down somehow or seized? Because obviously someone's going to have to own it, right? So there is like that point of attack for this giant reliance. How would you solve that then?
The funny thing there is that the validator is still the one voting and taking the decisions. So if you hijack the quantum computer, the only thing that you are hijacking is perfect finality.
Okay, you could revert back.
Yeah, it's like the quantum computer is not certifying that was actually the real one, and then you fall back to economic finality. But the quantum computer is only like delegated, and there are no trust assumptions there. That's the great thing. So the quantum computer doesn't vote directly, doesn't express any preference on the blockchain. It's just like saying, this is how this guy voted. I saw it, and I certify it. Obviously, everything is a bit more nuanced and we can go into details. But yeah, I think that in the worst case, we fall back to economic finality, which is what Ethereum already has now, basically.
Interesting. So how would you actually implement this? Let's go, if we wanted to put this into a validator, you can opt into it. And let's say it does, it uses a quantum computer, but then it gets shut down. It will just switch over back to the original state, right? So not perfect finality, but more economic finality.
Yeah, exactly. Like now, we don't really have the full details for that. Like you can say a quantum computer vote is this entropy thing that certifies blah, blah, blah. So, okay, right. If I don't see it, I do not consider this block final. And I do not consider, the last like n blocks final. until a quantum finalized blocks comes out. And hopefully that is every single block. But yeah, if the computer gets like DDoSed or stuff like that, it may be down for a bit.
So then, does that remove like financial incentives for validators though? Having perfect finality?
No, I don't think so. Not necessarily. I think that what it removes in a way is the possibility of having some kind of like economic attacks. The whole idea behind the stability of blockchain protocols is this is what really crypto economics is about. Say, if you look at standard cryptography, right? You say, okay, why does AES work? It works because you have some functions that are computationally infeasible to invert. It's like, very simply, if you don't have the password to decrypt this file, it takes the life of the universe to decrypt it by brute force. And that's not feasible. This is not the property that blockchains have. And blockchain, like take Bitcoin, for instance. In Bitcoin, you can rewrite blockchain history. For sure, you start mining on the Genesis block and you do it. The problem is that there, the kind of incentive is economic. You're saying it's not that it cannot be done, it's that it costs so much that there is no rational incentive to do it.
Yeah.
But this doesn't potentially defend you from very rich, very irrational individuals in a way. So you can have like a bank or someone says, yeah, I want to bring this thing down. This is a threat to my business and I have a shit ton of money to waste on it. And potentially they could try. I mean, whereas with perfect finality, that's not the case. We know that the whole history of the chain will be secured up to that point for sure. So yeah, it's a very interesting topic in a way. And it's also instant finality. In theory, if the quantum computer doesn't get down or destroyed or something.
Instant finality. So would that mean like blocks just would not be 12 seconds anymore?
No, it means that as soon as the block is out, it's final. So for instance, in Ethereum, I'm not like super versed with the inner workings of POS Ethereum, but basically you can still have reorgs. And then what happens is that every epoch or so, some stuff runs and basically the protocol tries to finalize up until some epoch. And at that point you say, okay, everything up until this epoch is final and everything else is, passive to, you can have reorg attacks. And we know that that's very bad for MEV and stuff like that. Whereas instant finality means that as soon as the block is out, the block is final. So it cannot be changed. You cannot have reorgs in any circumstance ever, which is very, very cool. By the way, Tendermint is also instantly final, but the point is that that's economic finality. So again, it's final under a series of economic assumptions, basically.
There must be some kind of limitations of one-shot signatures. Like, it can't. There's no way it can just be perfect. So what are the trade-offs? What is limitations, the challenges of implementing it, and what happens to, like, what does it bring? We've covered the positives. What about the negatives?
Yeah. So basically, the main challenge is that quantum computers are still in their infancy. There is a lot of progress being made. It seems that Moore's law is true for quantum computers. So basically, they are like exponentially getting better, but it's still very early. I think it's akin to, having computers in the 50s that were like giant rooms full of wires and shit, and you had things with the holes to program the things. It's like horrible, horrible stuff. It's more or less like that at the moment. And there are different ways of doing quantum computing. There are, people that do photons, people that do ion traps. There are different kind of technologies to do quantum computation. But for instance, one thing that is a problem is what is called decoherence. So that basically means that, to do the kind of quantum computations, you need to have a quantum state and to preserve that quantum state. Now, quantum mechanics is something that happens at the microscopic level. It's very fiddly. And basically, every time the kind of underlying environment slips in your quantum state, the quantum state becomes classical. We say that it decoheres, so it loses the quantum properties, and then you can't use it anymore. So at the moment, it's really funny because the way computing is like racing on a car that keeps losing pieces as it goes. And so the kind of goal is to be able to finish the quantum computation before this fucking thing loses the wheels and the engine and everything. And then it breaks down completely. So it's really like a very weird situation now. And there is a lot of effort in making these quantum computers to hold coherence as much as possible for related reasons. Another problem is noise. So sometimes it's not like the computer decoheres fully, but again, the underlying environment, the surrounding environment slips in and it introduces noise in your quantum resources, and this fucks up the algorithm. So there is a lot of like error correction that needs to be done to avoid that. And this is why there is basically a difference between a physical qubit and a logical qubit. So a logical qubit is a qubit that you see in an algorithm when you read theoretical stuff. A physical qubit is a qubit realized in a laboratory, in an actual lab. And basically, these two things are usually not connected. Since the physical qubit is prone to noise, there is a lot of like study in realizing a logical qubit by using multiple physical qubits so that the redundancy spreads the noise around and this noise becomes less hurtful to the quantum computation. So to produce like one good logical qubit, you need n physical qubits. And depending on the technology, this can be more or less noisy. But basically, long story short, the main hindrance that we have at the moment is that we need to compress, we need to optimize these quantum algorithms so that they become feasible, they become implementable as soon as possible. What you usually do when you write down a quantum circuit that represents, in our case, like quantum one-shot signatures or whatnot, you measure this circuit by, for instance, counting how many Toffoli gates you use. Toffoli gates are basically, quantum gates are kind of difficult to produce in practice. So the more you have, the worse it is. And then if you have like, I don't know, this many Toffoli gates, then you can estimate that you need this many logical qubits to implement the thing. And then you can estimate that depending on the technology, you will need this many physical qubits to actually do it. And then you see, okay, how many physical qubits does this computer have? Not enough. And so there is this kind of work of simplifying these circuits so that they have the least number of Toffoli gates or problematic gates so that they use less resources and can be implemented more easily, basically. So that's one of the problems. The other problem is that these quantum one-shot signatures rely on things that are still not completely proven to be cryptographically secure.
Would it even be quantum resistant though? Because if it's
Yeah, so exactly. So, okay, let me try to explain a bit more in detail how this quantum one-shot signature stuff works. So imagine it like this. You have a hash function, a classical hash function, like imagine SHA-3 or something similar. So you put some X in, you get a Y out. Very nice, very cool. Now, there is a procedure to turn any classical function into a quantum thing, a quantum unitary that is basically something that can be implemented in a quantum computer. The way this works is that basically you have things on two registries. The registries, you have to think about a registry in kind of the classical computing sense. It's like you have two registries that are like 10 bits long. This means that you have like 10 zeros on the left and 10 zeros on the right, right? So what you do is you start with the registry on the left that represents the input of your hash function, and the registry on the right, it represents the output of your hash function. So what you do is you set the registry on the right to 0, all zeros. The registry on the left you can use quantum entanglement, and basically this registry is now probability distribution, a uniform probability distribution over all the possible inputs. So if we do the simple case, we just have 4 bits in input. Then basically you take a superposition of those, and you're saying my state can be 50% 0, 0, 50% 0, 1, 50%, 25% 1, 0, 25% 1, 1. So it can collapse to anything. Okay. Now you apply the quantum unitary corresponding to the hash function. And what you get is that your input stays the same, is the usual superposition. And your output now is a superposition of all the possible outputs. So this thing can collapse to any y output of the hash function with the same probability. Now you measure the second registry. So you are actually saying, okay, I want to actually get something, a real classical value here. You measure and you get a y. So you get basically a bit string. Now, since the first and the second registry are connected by the fact that they are the input and the output of this unitary, as soon as you observe and you measure the second registry, the first registry that was your inputs, that collapses to a uniform superposition of all the pre-images of that thing. So now your inputs are not everything possible, but only the things that hash to y, all of them.
All of them.
All of them at the same time. Is a probability distribution. So you don't have one value. But now, if you measure this registry, you will get for sure one pre-image that hashes to y. You don't know which one. Now, up to here, okay, why is this useful? This is useful because at that point, we can use this thing before we measure on the first registry, and we run something called Grover search, which is basically a quantum algorithm that takes this uniform probability distribution and boosts the value of the pre-images that you want. So you say, among all these possible pre-images, give me the one that is formed by the validator message plus some random entropy. Give me all the possible inputs that begin with the validator message hash, basically. And Grover search is basically boosting the probability of the one satisfying this query among everyone else, everything else, so that when you measure, you will obtain exactly one pre-image like that with overwhelming probability. And that is basically what allows you to compute the pre-image after you compute the hash. But you can run this only once because, again, when you measure, this registry collapses to just one value and you cannot recover what you had before. There is also a theorem in quantum computing that is called no cloning that basically says that you cannot copy quantum information. So you cannot even make a copy and store it and use it again later on. All this stuff you cannot do.
So you can never do some Merkle tree or any of that?
Yeah, no, you can do exactly something, this stuff you cannot do. Now, this is how the algorithm works in a very hand-wavy way. The problem is that to run Grover search successfully, to implement it, you cannot just use any hash function. Because if you use a quote-unquote traditional hash function, then understanding how to run Grover search on it is as hard as inverting the hash, basically. So it's unfeasible. What we need to do is come up with something that can be used. We built a graphically non-secure hash function that works, that can be found on the QSIG Commission wiki on GitHub. And now the first task, we have two tasks at hand, basically. The first is estimating how many quantum resources we need to implement the cryptographically non-secure protocol, just to have a benchmark. And then we have to throw a cryptographic obfuscations the techniques to this hash function so that it becomes cryptographically secure. We need to cryptographically harden it. And exactly as you mentioned before, we cannot just use any obfuscation method. We need to use quantum resistant obfuscation methods.
Yeah, if you have quantum computers to do, one-shot signatures, then you're going to make sure that they're resistant as well.
Yeah, to invert them. Exactly. And these are the research. This is the research that we're doing at the moment, basically. Yeah, so we need to have proofs of security of these things. In cryptography, it's common to prove that some cryptographic thing is secure within some probabilistic margins, or you say,
right.
An attacker that has this and that will not be able to break this thing with overwhelming probability and stuff like that. So that can be proven. But the interesting thing is that quantum circuits can be simulated on a classical computer. The problem is that this simulation is usually exponential in the number of quantum gates. So you can definitely simulate a quantum computer on a classical computer. The problem is that it's exponentially harder computationally, which is, by the way, the reason why we need quantum computers. Otherwise, we wouldn't need them. So yeah, we can run simulations and stuff.
So quantum computers basically allow you to get to exponential computation.
In some cases. So there are things that quantum speed up. I think that the most well-known one is probably Shor's algorithm that allows to factorize numbers very efficiently. Basically, it takes a problem that is exponential in time in classical computing, and it computes it in polynomial time. Shor is very relevant because it's basically the reason why people say that quantum computing breaks elliptic curve cryptography, discrete log problems, and a lot of the cryptography commonly used today. But there are other things that, are not quantum weak. For instance, hash functions, SHA-3, SHA-256, whatever it is, that works with a purely combinatorial principle, and there is no reason to believe, at least to my knowledge, that a quantum computer may give you an advantage in breaking that. So when people speak a lot about post-quantum cryptography, and the idea of post-quantum cryptography is classical cryptography where quantum computers have no advantage. By the way, about that, there's a friend of mine called Pierre-Luc that he released a count abstraction implementation on Ethereum. I think it's on testnets, probably Sepolia, I don't remember. And it's a wallet that is a quantum resistant wallet. I don't remember the name. I'll probably give you the name afterwards. But basically, it's a smart contract because it's a count abstraction. And this smart contract basically allows you to use a signature scheme that is quantum resistant. So you can control this smart contract by issuing commands, let's say, by calling functions, but these functions need to have a signature that is not the usual Ethereum elliptic curve cryptography. It's quantum resistant. And I was mind blown by the fact that these guys were able to, implement a quantum resistant wallet without changing the protocol by one bit. There is no protocol change involved at all. They just deployed a smart contract and that's it. And now you can secure your own assets against quantum computers in the future, which is great.
When do you think actually quantum computers are going to be viable, where I guess it's not an everyday thing to at least a laptop, but a fair few people have them and it starts becoming a threat, but even a new revolution in computing?
Quantum cryptography, there are a lot of papers coming out all the time with new estimates and stuff like that.
Yeah, very ballpark.
Yeah, the most optimistic people I've spoke with, they say 5 years. I find it very optimistic, but it's not that far away as people think. I don't think it's 2050. It's not 5 years, probably that 10 years. May be likely. If we keep going like this, it may be likely. And importantly, there are different approaches to quantum computing which scale differently. So for instance, there is this approach called photonics, which basically uses light particles to do quantum computing. These has some big problems in terms of that you need very precise optics to do some of this stuff. But some of these approaches, it's clear that if they crack the way to do it, then scaling becomes very easy. And at that point, you can go from 10 qubits to 1,000 qubits in a matter of months, not in a matter of years. So again, it depends on the approach. But some of these, I mean, theoretically, tomorrow we could see a breakthrough and suddenly I would have to revise my estimate and tell you, change all your fucking curve crypto because like in 2 years, this is going to go down the drain. That would be catastrophic.
I think if quantum computing became like a thing, then quote unquote AGI would be much easier to do as well. So it'll be like in parallel, like everything just exponentially grows. That requires computation at least.
Yeah, I don't know the detail. I know that there is a lot of work on quantum machine learning, but in general, I mean, I may be wrong here, but I think that one of the reasons to believe that quantum computing could really be an advantage for artificial intelligence is that quantum computers are really good at doing linear algebra. And in the end, all these neural network stuff, tensor networks, whatever, they're just like huge systems of huge matrices that need to be multiplied, inverted, and rewritten all the fucking time. And this can be natively like done in a quantum computer. So, yeah.
Interesting. I remember looking at quantum computing before, and I was like, how do I make one in my bedroom? They just seem like really cool because I got into electrical engineering. I'm like, what's the next step? Quantum computing, FPGAs, what's next? Give me in at all of them. Very interesting. I mean, like if quantum computing came around and it was like very viable, multiple people having them, I mean, normal cryptography would be so wrecked. How do you actually get normal cryptography to be quantum resistant?
Well, you change cryptographic scheme. As I said, for instance, hash functions are, not all of them. Like Petersen commitments are quantum weak, but like combinatorial hash functions are fine. I think AES is also fine. What you need to do is basically to replace everything that depends on like a discrete log problem or stuff like that with something else. But for instance, there are quantum resistant approaches to zero knowledge proofs. And indeed, one thing that I don't understand is why, projects like Ethereum are literally investing millions of dollars in researching zero knowledge proofs in a way that is heavily dependent on elliptic curves. Also, like all the stuff that is, being done now about vector trees for, Ethereum state and stuff like that, heavily dependent on Petersen commitments. And for the love of God, I don't understand why. Because, I mean, I understand if there was already something and then, it's okay, we chose this path. But, I mean, if you have to start from scratch, what's the point of accumulating technical debt, knowing that we'll have to redo everything in a few years anyway? We'll have to rechange all this stuff. I don't know why they're doing it like that. I mean, it's not my business for sure. But yeah, I think there are ways of doing it. Like, zero knowledge proofs that are not based on elliptic curves, for instance, you can have zero knowledge proofs using a modification of a Reed-Solomon error correction thing. So I'm not very knowledgeable about this, but imagine that you know how error correction works. That when you have a QR code and it's partially destroyed, you can still scan it. There is basically an algorithm that is usually Reed-Solomon that introduces strategic redundancy so that if up to 20% or something of the support is destroyed, then you can still read it. And you can weaponize this to do zero knowledge proofs by basically taking the whole thing and introducing redundancy and then destroying the parts that are important in a way so that you can kind of scan the code and so see that, the proof is valid without really knowing what the code is talking about because the code has been destroyed purposefully in a way that you cannot recover the original information. You cannot learn anything about the original information. And all these kind of things are quantum resistant. that there's stuff to be done. The most interesting thing, this is an opinion that also Justin Drake has, and I share it. The interesting thing about quantum Washer signatures is that every time you hear about quantum computing and cryptography, it's always a very defensive posture. It's always, oh, this computer will come and will destroy all our cryptographic primitives, and so we need to implement something to defend ourselves against it. And instead, it turns out that if you use it in the right way, quantum computing gives you a lot of power and advantages. So I really like that quantum Washer signatures are, in a way, optimistic. They do not see quantum computing just as a threat. They see it as a potential. Say, okay, we can use this thing and have perfect finality. Great. We didn't have it before. So there's something to gain. It's not just like, defending our position. We can use these technologies to have a better blockchain, a better Web3. And I really like this optimistic way of looking at quantum, which is very niche in our field, for what I know.
Yeah, 100%. I really want to see this getting implemented, though. And you said you're working on implementation as well. How's that going? Are you getting close? Do you have the architecture, the design ready? Still working on it. What's the hardest challenges you're facing right now for preventing full implementation?
Well, as I say, the hardest challenge is not depending on us. It's that the quantum computers that we need are not yet there. But the biggest challenges that I'm seeing at the moment are, again, making what we have cryptographically secure, so cryptographic obfuscation, and optimizing these things as much as possible. By the way, the optimization stuff is something that we already saw in this space. I don't know if you remember, but like 5 years ago, I really remember a lot of people saying zero knowledge proofs are bullshit. They are totally useless because there's no way you can put the EVM inside an arithmetic circuit. You cannot producing a proof of an EVM smart contract will take the life of the universe. This is not usable. And in the last 5 years or so, a lot of people put a lot of effort in simplifying these circuits so much that now we have things like ZK-EVM. And if you really try, you can find it. So it's funny that before in January, when we had this QSIG workshop, there was no cryptographic function. Like these quantum Washer signatures were constructed in a very non-constructive way. There was a proof that said that they existed, but no one basically produced one. Then we produced one. And then another group produced one. And in a matter of like 3 days, we go from no implementation, no model, to a model that needs, I think, was like 1 billion Toffoli gates, which is a shit ton of Toffoli gates, to another model that is the one that we have on the QC Commission wiki that needs 1 million Toffoli gates. So in 3 days, we went from no constructive proof to 3 orders of magnitude improvement in optimization on the same construction. Literally 1000x betterment in performance. I mean, for me, that's good progress, right? So yeah, it's just a matter of keep pushing until we
accelerating.
Yeah.
What do you think is missing from current quantum computers that are like limiting us to actually having them at a viable state where a lot of people have it, or at least that's the level that you want to see them at? What do you think's missing?
In my opinion, the problem at the moment is not really a software problem. There is a lot of research going on in quantum algorithms and stuff like that. It's a hardware problem. It's a problem of materials. It's a problem of, physics of materials, like engineering techniques, literally.
Yeah. And the hardware is seen as very expensive as well, which is, like I think NVIDIA has a market cap of like 2 trillion. Just insane.
Yeah, it's super expensive. Like I know for a fact that some quantum companies out there that do hardware, they have burn rates of like 150, 100, 200 million per year.
Oh my God.
Yeah, it's super expensive.
Insanely expensive.
It's like for our standards in crypto, that's unbelievable. Yes, absolutely. you need the facilities. You need these like hyper precise prototypes. You have to commission like to lenses builders, for instance, like Zeiss or something like that. These lenses are insanely expensive. And then you need a lot of different experts in different things. So you need to pay a shit ton of salaries. I mean, it is a very expensive business. But indeed, the main purpose of quantum software at the moment is that people are writing algorithms. They are finding better ways of doing things and they are patenting them. Like the whole business there is when these computers become viable, we have the patent for this algorithm, and then people they are basically squatting quantum algorithms. That's a big business.
Well, hopefully soon we can see them. Hopefully someone has a breakthrough and we can actually see something. Maybe NVIDIA, maybe someone else. It'll be such an interesting future once, quantum computing is then in play.
NVIDIA, I don't know how much they are involved in quantum computers. I think that
I'm sure they'll pivot in some way.
Could be. The bigger players at the moment are, I think, Google, Quantinum, IBM, PsiQuantum, Quandela. There are a few companies. The good thing about obviously like companies like IBM or Google, they have the advantage that they have a cash cow. So, even if IBM Quantum can basically afford to burn money forever, whereas a company that is solely quantum focused, they must be way more aware about how to use their funds, and they have to do like investment raises, stuff like that. So that's a big difference in how the business is conducted.
Well, I'm super excited to see how the future plays out. I've learned a fair amount from the quantum realm from you, my friend, and I'm sure this is a very unexpected podcast for the normal listeners. So.
I guess it's interesting. By the way, if you want to know more, we'll probably have something about it next ECC, most likely at DevCon in Bangkok. I'll probably organize something also in Naples. We have an event here called Napulet in September that I'm organizing. So I'm trying to sneak a bit of quantum in crypto every time I can. So
you're pilling everyone.
Yeah, I'm trying.
Trying. All right, man. Well, I don't want to take too much more of your time. We're definitely going to have another one in the future when things get more spicy, more on the implementation side. We can actually see it in practice.
I really hope.
Yeah, same. I'm waiting for you to make this breakthrough. But Fabrizio, man, it's been such a pleasure. Thank you so much for jumping on. I'm going to have you on again later.
Okay, thank you. Pleasure mine. See you then.
All right, man. Take care. Thank you, everyone, for listening.